Have you ever wondered why radiation, something so invisible and intangible, can have such profound effects on the physical world? Welcome to the intriguing domain of radiation physics, where we'll delve into the mysteries of this fascinating phenomenon. Radiation physics might seem intimidating at first, but think of it as a symphony. Each instrument, or in our case, each particle and energy wave, plays its part to create a harmonious, albeit complex, melody. First, let's think about the players in our symphony, the particles and waves. These include alpha particles, beta particles, gamma rays, and X-rays. Alpha particles are like the heavy bass notes, large and charged. They can't travel far, but they pack a punch. Beta particles, on the other hand, are smaller, lighter, and can reach further distances. Gamma rays and X-rays are the high-pitched notes that can pierce through almost anything, making them incredibly penetrating and potentially dangerous. Now, consider the concept of ionizing radiation. In music terms, this is like the crescendo, the point where the energy of the radiation is so high, it can knock electrons out of their orbits around the atom, causing ionization. This is where radiation can start to have significant effects, especially on living tissues. The concept of radiation dose is another crucial part of our symphony. This is how we measure the amount of radiation absorbed by an object or person, like measuring the volume of our music. It's not just about how loud the music is, but also how long it plays for. Similarly, both the intensity and duration of exposure to radiation contribute to the radiation dose. Now onto radiation protection. It's like soundproofing in our symphony analogy. There are three key principles: time, distance, and shielding. Minimize the time exposed to the source, maximize the distance from it, and use appropriate shielding materials to absorb or deflect the radiation. In radiation therapy, these principles are applied to maximize the dose to cancer cells while minimizing the dose to healthy tissues. This delicate balancing act is akin to a finely tuned musical performance, requiring precision, skill, and a deep understanding of radiation physics. So what have we learned today? We've discovered that radiation physics is like a symphony, with different particles and waves playing their parts. We've understood that ionizing radiation is a powerful crescendo that can cause significant changes at the atomic level. We've learned that the radiation dose is like the volume of our symphony, determined by both the intensity and duration of exposure. And finally, we've seen how the principles of radiation protection are applied in radiation therapy, like soundproofing in a concert hall. Radiation physics is a complex, yet fascinating field. And just like a symphony, it requires careful orchestration and understanding. But once you start to appreciate the beauty in its complexity, you'll discover a whole new world of possibilities. Remember, the world of radiation physics isn't just for the scientists in white coats. It's a melody we're all part of, shaping our world in ways we can't always see. So keep exploring, keep questioning, and most importantly, keep learning. Because the more we understand, the more harmonious our symphony can become. Welcome back. Now that we've covered the basics of radiation physics, it's time to dive a little deeper. In this scene, we're going to explore the different types of radiation and their sources. Radiation, in its simplest form, is energy moving from one place to another. Imagine it as the notes of our symphony traveling from the orchestra to your ears. But not all notes are the same, and neither is all radiation. First, we have alpha radiation. These are the heavyweights of the radiation world. Alpha particles are like the deep, resonant notes of a double bass. They're big, powerful, but they don't travel very far. In fact, a sheet of paper or a few inches of air can stop them. Natural sources of alpha radiation include radon gas and the decay of heavy elements like uranium and thorium. Next up, we have beta radiation. Beta particles are lighter and faster than alphas. They're like the agile notes of a violin, able to travel further but still easily stopped by a thin sheet of aluminum. Common sources of beta radiation include strontium-90 and carbon-14, which is used in carbon dating. Lastly, we have gamma radiation. These are the highest energy radiations, like the piercing notes of a flute. They're not particles but waves, and they can travel great distances and pass through many materials. Gamma radiation is emitted by many radioactive materials, including cobalt-60, and is also produced in nuclear reactions, and by certain types of high-energy equipment. Whether natural or man-made, these types of radiation are all around us. They are part of our symphony of life, playing their parts in harmony with the rest of the universe. Understanding them better helps us appreciate the melody and rhythm of our world, and better equips us to navigate it safely. So let's keep exploring and keep learning. The symphony is far from over.